Hello everyone, my name is Bin Chen. I am a postdoc at Max Planck Institute for Informatics. I will be presenting our work, Gloss Management for Consistent Reproduction of Real and Virtual Objects. Firstly, I would like to highlight the significance of gloss consistency. A good match of material appearance between real-world object and their displayed version is critical for many applications. For example, when exhibiting the cultural heritage on display, we want to fully reproduce the beautiful appearance of relics. Or in industry production, it is sometimes annoying that the manufactured products looks different from what you design on computer monitor. Or another example is the furniture preview application on augmented reality devices. We want our final purchased furniture looks the same as what we previously previewed, I believe. But the reality is, in most situations, there is an appearance discrepancy between the real-world object and its displayed counterparts. Arguably, color and gloss are two main factors that influence the appearance perception. Of course, other factors like resolution, contrast, stereoscopic, motion parallax, and maybe accommodation may also matters here. But things like resolution is already beyond the retina capability in the consumer level displays. Other factors mentioned here are inherent feature of 2D displays. There are already several works studying the color consistency between produced object and displayed image. In this work, we would like to study this problem on glossiness. So I hope that I may convince you that the gloss consistency really matters. So in general, the goal of this work is a step forward to understand the gloss discrepancy between real objects and its displayed version. Our contribution lies in, firstly, a large-scale psychophysical experiment that considers many factors inside. Then we did a deep statistic analysis on the collected data. Based on that, we got a lookup table to compensate for the gloss discrepancy. And finally, we show two real applications in fabrication. Let's look into our experiment. Firstly, I would like to talk about our stimuli. For geometry, we select 4 models that are pretty commonly used in computer graphics community, like the bloop, Stanford Bernie, and dragon here. The geometry A, we call it ghost because it looks like a ghost. This one is optimized for perception study, so we also include it here. Moreover, we show that these 4 geometries cover a large range of surface features based on our surface curvature analysis. For the illumination, traditional experiment setup usually letting user make judgment based on observation from a very small light booth. But we would like to do our experiment in kind of natural view conditions. So we build a room-scale controllable environment. Firstly, we use a diffuser to cover all space to produce a kind of uniform light. Then we use spotlights to simulate the different complex level of light sources. Here is the captured environment map. By default, we have a diffuse light without turning on any spotlights. And another one is 1 spotlight, 3 spotlights, and 5 spotlights. For gloss levels, we depend on the 3D printing technology. We firstly print a large number of models using the geometries that we just mentioned, the 4 kinds of geometries, and then paint them with matte black as the base color. Then we mix the glossy varnish and matte varnish together in different proportions. In this way, we can create different level of glossiness, right? And then dip the 3D printed model inside these varnish mixtures. Finally, after air drying, we got these results, a large number of models with different gloss levels. We also test the influence of different brightness level of display because the results might change when you're using different brightness level for display. Here we use three levels, the bright one, the medium, and the dark, to represent three typical scenarios. The first is daytime in office, second is nighttime, and cinema environment. In order to make the display faithfully reproduce the luminous level of the real world, we measure data in these three brightness level and feed into three gamma offset gain we call GOG display models. Note that we also consider the monitor surface reflection in this GOG model. We finally capture photograph as stimuli and show them on monitors. In order to cover all the luminous level, we capture photos in 13 exposures and then fuse them together to HDR. Then do the chromatic adaptation to 4000K, which is the white point of our light sources. Finally, we use the GOG model to convert HDR to LDR. In this way, we could achieve a pixel level luminous match. The luminous difference map is shown here. As you can see, most of the regions do not have differences. The mismatch only appear in some highlight regions that are too bright or black regions that are too dark. They are all out of the capacity of the display. You can also see clearly the overall luminous coverage from the distribution on the third row here. So finally, we have 4 geometries, 4 illuminations, 10 gloss levels, and 1 random brightness level. So in total, we got 160 trials for each user. We only randomly select one brightness level for each user because otherwise it will be too much to do for each person. We then calculate the best view distance and gesture based on the display specifications and keep them the same for all participants. Here is the simulated sense and the real user study in our setup. By adjusting the height of the chair, we make sure all users are looking from a very similar viewpoint. We allow users to use the display normally, like what they do in their office. So like a small motion parallax is allowed here. The matching experiments has been applied in our study. The task for user is very easy. Given a real object, user need to adjust the gloss level of the displayed image to match the real one. They need to do this back and forth until finding the best match. Okay, comes to the data analysis. We use multinomial logistic regression model for our data analysis. The factors we consider here are, of course, the illumination, geometry, display brightness, and their interactions. We got a good fit with R-square value equal to 0.87. Based on the p-value test, all the factors have significant effect, as well as their interactions. They all have the p-value smaller than 0.001. So let's check in depth on each factors. The x-axis V10 to V100 means the varnish mixture. That is also our gloss levels. The y-axis D10 to D100 means the displayed gloss levels. Naturally, the diagonal means real object and displayed version totally match with each other. However, the reality is not that ideal. For example, given an object with 20% gloss level, people select around 35% gloss to match with it. So we now see the discrepancy. When analyzed by geometry, the bloop, ghost, and Bernie behave like a group, and they are statistically indistinguishable. Dragon is different here. This might caused by its very complex and strong tessellated surface, because this will make the discrimination of very subtle gloss effect more difficult than the smooth surfaces. Correspondingly, stronger gloss correction is needed. But overall, the differences on geometry is not that obvious. For display brightness, we can see from the figure that the darker the display, the more correction is required. Well, this is something maybe not surprised and expected, right? I think our contribution here is to quantify the amount of discrepancy and the correction. For illumination, the diffuse light poorly exposed highlights means that you cannot see much contrast on object surface, so more correction is expected. A single spotlight behaves conversely. It produces very clear highlight patterns on object surface, so minimal correction is needed. 3 and 5 spotlights stand in the middle as a group. Highlight patterns are more complex now, and their overall contrast reduced compared to one spotlight. We also did an extra experiment on lightness under 2 illuminations. The diffuse light shown in green color, and the one spotlight is red in this figure. Only burning is used in this experiment. We have black, gray, and white, 3 different lightness levels. We find the correction on diffuse light decrease with lightness increase, and the white need more correction under one spotlight as shown here. This is something very interesting to us, since the lightness influence a lot in this problem. It's worth to explore more in the future to review the reason behind. So based on our correction, we demonstrate 2 applications. The first one is digital product design. In this application, we want the produced object looks the same as we designed our monitor in terms of the glossiness. First, we have the geometry, BRDF, and environment map, and we render the image out. We trace the correct parameter value in our lookup table. Then we mix the varnishes based on the corrected number for final object varnishing. We use another model to test in this application. On the left is the rendered image. In the middle is the photograph of produced object with 60% gloss level. On the right is the corrected one with 65.6% gloss level. Given these 2 real objects, we let user choosing the one that best match with the rendered version in terms of gloss. So the results show that most user will prefer the corrected in green color rather than the original version in red. This is only we only demonstrate the one spotlight here. Experiment under diffuse light show even larger preference can be seen in the graph on the right side here. In the next application, we do inversely. So given a real object, we want the displayed version looks the same appearance as real one. So we start from a real varnished object. We may scan the geometry, but here we already got the geometry, so we don't need to do that. We need to capture the illumination and measure the BRDF. You may wonder how do we measure the BRDF? For getting the BRDF, we use a very simple setup as shown on the left to measure the data from different angles. And then feed the measured data to an analytical BRDF model. Here, we use Cook-Torrance model with GGX distribution. We can find the fitting accuracy is very high as shown on the right. Finally, we can get the correspondence between brightness mixture and the roughness parameter of BRDF alpha here. Let's come back to the second application. After getting all the ingredient, we can again do the inverse searching in our correction model and find the correct roughness value alpha. And finally, render out the image that has the same glossiness level as the real object. Here, we also show an example under diffuse illumination. The user study results are shown on the right side. Again, most people will prefer the corrected version over original one, especially under this diffuse light. We should note here the figures, the Bernie 3 Bernie you are seeing here now is not the same as our experiment because you are also looking them on the display, right? If you are interested, please come to the interactive discussion session for details. Okay, I would like to conclude our work. Our current experiment may have some limitations. For example, we only test on LCD monitors with a limited dynamic range in office scenario and only test the plastic 3D printed object. The future work could be experimenting on HDR displays, maybe test other materials like metal, maybe test on reflective coating monitor rather than the matte coating. And another study on stereoscopic could also be very interesting. In conclusion, our work is the first step to gloss consistency between real object and its displayed version. We contribute the experiment, the data analysis, the correction model, and also demonstrate two real applications. For more details, please visit our project page. Thank you for your attention.